This is one of your samples, by the way, because I see I see like soldering on the outside of the plastic package or something for grounding, I guess, or
that is probably grounding. So actually, this is one of the many images in this presentation, which I Googled yesterday afternoon.
Okay.
So actually, this is also important because I'm going to be publishing this online. I've put all the image sources at the bottom of the slide. So let's say the topic that I want to tell you about today, at least, is at least my understanding of wire bonding. And so I've been, as I mentioned in our pre-discussion, I've been wire bonding for many years, and I have lots of experience getting bad samples to work in the wire bonder, but also making sure the wire bonding is working well. So, and my aim today is to share that information with my PhD students in the Steel Lab, so that they can also gain at least my understanding and knowledge of wire bonding. And we will also share this with our clean room so that we can propagate a bit more information through the clean room about how wire bonders work. So I'll be talking today not about a specific machine, but just about the concepts in wire bonding and how to understand how it works and what you can maybe do to try and fix it if something's not working. So actually, this is a very nice picture I found on the internet of somebody's sample in a recognizable chip carrier, which is below the tool of the wire bonding machine. And it's also a nice place to show you guys a little bit about, actually, I think I can turn on a laser pointer here. Yeah. So these are the different, you can already see here the different parts of the wire bonding machine. So this is what's called the ultrasonic horn. That is something that generates the ultrasonic power that actually causes the wire bond to form. This is what's called the tool. That's a piece of ceramic, precision machine ceramic, that has a little face on the end that you push into your sample and squish a little wire that you can see sticking out here against a metal pad on your sample. That wire is threaded through a tiny hole in this machine ceramic piece, and then it goes up to a spool of wire up there somewhere. And here you can see what are called the clamps, and those are some clamps, some little jaws that open and close depending on whether what you want to do with the wire. So I want to actually start with, before I go into the detail about at least my understanding of how that process works, a simplified understanding of how that process works, I want to also go and zoom out a bit and talk a little bit about different types of bonding. So if you Google wire bonding, there are sort of three main types. The first and actually most commonly used, is my understanding, in the semiconductor industry, is called ball bonding. That works in some crazy way where you have the wire feeds through the tool, and then you create a spark that melts a little ball, and then you squish that into your sample to make the bond. It looks like this. When you use a ball bonder, you get little wire bonds like this. And actually the second bond is actually an ultrasonic bond, like what we'll talk about in a minute. So ball bonding is cool and effective, but it's not what I want to talk about, because we don't typically use ball bonding in our applications. So what we would typically
sorry, Gary, why is that? Why don't we use ball bonding?
Good question. I don't know.
I know it's you need to preheat your sample also a lot, because this is gold. You typically almost always ball bond with some sort of gold wire, and it's much more problematic. Also, depending on what you want to do, because you guys also use it like cryogenics. Well, of course, your other wire can go superconductive. So that's also maybe the reason why. So you need to have more infrastructure in place to get ball bonding because it's gold wire. Remember, you need to preheat it, and the sticking capabilities is it's more hard to get a good bond. Let's say that.
Okay.
So what the process that we use is that the typical bonders I've ever used is based on what appears to be often referred to as ultrasonic wedge bonding. And there, the way it works is that you have some wire, in this case, a copper wire, because I took this paper from a paper on copper wedge bonding. But typically, in our case, it can be gold. I use gold wire a lot when I was at MIT, and then we did, in fact, heat our sample a bit. But it could also be aluminum, which is what we often use these days, just for various reasons. And the way it works is that both of the bonds are formed by a process called ultrasonic bonding, where the wire is pushed down from the top with a force, and then the system applies an ultrasonic vibration that causes this wedge to jiggle back and forth. So this is some, again, pictures that I've Googled from online of what an ultrasonic wire bond will look like. So in contrast to the ball bond, where there was this ball and the wire goes straight up, it typically has this sort of little flat, squished out section. And then you can, depending on how you move the wire through from the bond 1 to bond 2, you can make bends or kinks in it a bit, hopefully not kinks, but bends in it. And then it goes down to the second pad where it also makes a second bond. Good. There's a third type of bonding called ribbon bonding. Actually, this is an example of heavy ribbon bonding, but it made a very nice picture. And that's my understanding of ribbon bonding, is that it works very similar to ultrasonic wedge wire bonding, but then with a ribbon instead of a wedge. And this is a bit more specialized. It's quite often used for radio frequency stuff because it gives you a nice low inductance contact, but it requires a little bit more specialized tools and stuff. And that as far the Westbond, I think, makes ribbon bonding tools and ribbon bonders, but we typically work with wire bonders. So I want to go a little bit into at least my understanding of what actually happens when you make the bond. I've drawn another copy of what we saw before. So this the basic important things are the tool, which is this piece of machined ceramic, which has a little flat section on the end. And actually, sometimes this is quite often concave, sometimes it's flat. There are different types. Sometimes it can be notched from the company that sells these tools. You can buy all sorts of different shapes of the tool on the end, but more or less, it's got some sort of place that pushes down, and it's got a hole in it through which the wire is threaded. And this wire, the idea is that this wire is threaded through the hole from the back of the tool, and it goes underneath this little pusher part of the tool, and it comes out here, and this is typically called the tail of the bond. And now the process of making the bond itself, it corresponds to the formation of a bond between the metal wire and the metal pad that you're trying to contact. And the way that works, as I described already a bit before, is that you apply a force vertically downwards on the tool. In the Westbond machine that I worked with and that we have in the clean room, this is done by having basically a little mass on a screw cantilever, and you can calibrate the force using a little tool that measures the force, and then you screw the mass in and out to adjust it. Jason has a fancy machine that can even dynamically adjust the force.
I still calibrated with my coffee scale machine from home.
Oh, okay.
To be sure, but yeah.
It's somewhat fancier machine, let's say. So the first step is that basically you just push this down, and actually the way the Westbond works, as soon as it touches and it has the weight of that cantilevered mass pushing on the wire, that triggers the ultrasound switch. And then, so once it's pushing down with the specified force, it turns on the ultrasonic horn, and the ultrasonic horn actually makes standing waves in the tool. But the upshot is that in the end, the tool starts to wiggle back and forth. It literally, it's like kind of smearing the wire into the metal. It really is making what's important is that it's actually making a horizontal sliding motion on the substrate. it actually typically apparently applies enough force that the wire does not actually slide on your metal pad, and it forms some sort of place where the ultrasonic power is dissipated in some complicated physics. But the upshot is that more or less it kind of goes down and goes like this. It just kind of rubs the wire into your substrate. And if it does that in the right way, then it can cause the metal of the wire bonding wire to fuse with the metal of your metal pad. And that makes the bond. And that's pretty much all there is to it at some level.
Keep in mind that it's handy when you're designing your samples that the intermetallic layer is about 11 nanometers. So if you have multiple layers, if you want to have certain oxides or whatever, you don't want to go through it, make sure that it's thicker than 11 nanometers. I found out the hard way.
Interesting. So that's the basics of the process of using the vertical force and the horizontal wiggling to form this intermetallic bond between the wire and the metal pad. Now, there's one part that I haven't even talked about yet over here, and that's the clamps. And the clamps don't really have a role in forming the bond, but they have a role in what happens after you form the bond and lift up the tool. And in particular, in a typical machine configuration, there are two settings. There's a setting for the first bond and a setting for the second bond. And the difference between the first bond and the second bond is what happens to the clamps after the bond has formed. After the machine is finished applying the ultrasound, it does something with the clamps. And what it does depends on whether you're on the first or the second bond. So if you're on the first bond, then what happens is that the machine actually has the wire clamped during the bonding. And as soon as it's done applying the ultrasonic pulse, it will open the clamps. And what then happens is that when you lift the tool, or if you're an automated machine, when the machine lifts the tool for you with a motor, it will, since the wire is bonded to the metal pad, the upwards motion of the tool and the clamps and the tool move together, will pull the wire through the tool and the clamps. And so it's actually like the chip is threading the wire through the tool and clamps. And that actually requires quite some force on well, actually it depends on how dirty your clamps and your hole of your tool are. But it can require quite some force on the interface of the metal wire and the metal pad, which is actually why it's sort of why sometimes if you have a very bad bond, it's better not to do your first bond on a weak metal surface, because that one actually involves the most pulling of the wire when you're lifting the tool after the bond has been made. So then when it's going to the second bond, when it's making the second bond, so imagine this is actually going up and connecting to the wire over there, then you want to actually break the wire off. And the way that works is that after it has applied the pressure and formed the bond, it then closes these clamps. So the clamps are then, as soon as the ultrasound is finished, it clamps the wire, and then it starts to lift. But because the wire is clamped, what it does is it pulls on the wire that is attached to the metal pad. And now here's the crucial bit. Hopefully, what you typically want to happen is that there's typically going to be a weak point at the corner of the place at the edge of this bond where the wire's gotten squished and a bit thin and a bit weak. And then the idea is that as you pull the wire up, it will generate some tension in the wire. When that tension is high enough to break the wire, it will actually tear the wire. And then that will break the wire off after the second bond. Yeah, there's actually, I was reading yesterday, there's actually some machines that apply a table break, it's called. Where
table tear.
where they
Call it
where they
temperature.
apply on purpose a horizontal motion to sort of slice the wire off with the tool before they pull it up. And that's also a trick I sometimes do on the manual bonders if I'm having trouble with the adhesion, because the whole, one important point is that if you have a very bad adhesion problem on your metal pad, then you don't want to apply a lot of force to your bond when you try to pull the wire up. And so if you can already kind of break this bond or make it all a little bit squishy to start with, then that will make your life a little bit easier. But if you have a normal metal pad and good adhesion, then actually none of this matters. And as long as you get the bond settings right, it should just always work. Okay, but the important message I want to get across is that there's basically two different ways of there's two different types of bonds. There's the first bond and the second bond. The only difference is, from the machine's point of view, aside from any different parameters you program for first and second bond, is that the first bond, the clamps open after the bond is done, and the second one to allow the wire to be pulled through the tool as the tool lifts up. And then the second bond, it closes with the intention of tensioning the wire and snapping it off.
If you have a fancy system, you can also have something, they also call it ribbon bonding. You can go hoppity, hoppity, hoppity all the way around.
Oh yeah, yeah.
It's also very nice if you need to ground, or if you have a global back gates or multiple gates, you will need to gate at the same time.
Yeah, you can actually basically repeat your first bond.
Yeah, it's very nice, very handy.
Okay, questions so far? Is that super clear to everyone? It's really obvious, makes sense. Good. So, how do you know if you've done the job right? This is just purely out of experience by doing a lot of bonds and looking up some in some books. Actually, I found this PDF on the web yesterday. It's a very, very useful PDF. I recommend it actually for reading, and from it I stole this beautiful image. There's sort of my personal experience is that basically you want a pretty good squish, but not too much squish on your bond. So if your bond wire, you can actually, this is an electron microscope, but typically the optical inspection microscope on the wire bonders is good enough for you to see this visually with your own eyes while you're bonding. It should be kind of squished. And my rule of thumb that I always guesstimated was that it should be about a factor, from the top, it should be about a factor of 1.5 to 2 times bigger than the wire diameter. So you push down, it squishes outwards, and it should be about 1.5 to 2 times larger than the wire diameter when you look through the microscope. And that's an indication that you got the bond in about the right configuration. If you want, there's actually even a table of these ratios in the PDF below. So what are examples of bad bonds? So these are also from the PDF, and these are cases where the bond has just become too squished. So if the power is too high and you've applied either too much force or too much power, then the wire gets too far flattened. And then if the wire is too far flattened, then it can sometimes look like this, and you can get this very weak point here, which will be very susceptible to breaking off. If you needed to break off, that can be handy, but if you generally don't want your wire bonds to break off, and so you want to avoid squishing them too much. In addition to the risk that your wire bond will not stick or will break off, actually it's not that your wire bond is not sticking, it's that your wire bond is breaking off. In addition to the risk of the wire breaking off, this higher power and force also has an associated risk of damaging your substrate. So I used to bond on 200 nanometers of silicon oxide, and I knew that if I put the wire bonder power too high, then I would often end up with shorts at lower voltage across my oxide, for example. So this leads to the how to know if you've got the parameters right. This is sort of my illustration of my personal experience changing the power in the bonder. And my experience is that if you put too little power, then you just get, you typically see a few little nicks on your wire. It's not really squished at all. and it actually doesn't stick to the metal pad. So if you lower the power enough, if you put the power to 0, then then the wire doesn't bond, right, at some point. And so there's a one extreme here where the wire just doesn't even stick to the metal at all. There's what I call the good zone, where the wire is squished by about a factor of 2 or so. If that is at a higher power, and if you go to too much power or force, then actually it gets really fat and wide. And what's an super important point to make is that the exact power settings you need to reach the good zone are very much dependent on the type of metal pad you're bonding on. If you're metal bonding on a sort of big, squishy, gooey, 50 micron thick gold on your ceramic carrier, you will need a different power than if you're bonding on, say, 30 nanometers of platinum on a silicon substrate. And that's because it depends also very much on how soft the surface is that you're bonding, how the power translates into a squishing. So it's not that there is like a single set of good powers that you program once on the machine and you never touch them again. My personal experience is that for every different type of material I was bonding, I would find this sort of optimal good zone power at a slightly different power threshold, and sometimes very different power threshold. And also my experience on working on many machines is that these numbers are not absolute and they can drift in time. And I've often wondered why they drift in time. And one of my personal feelings is that it probably has to do with how the tool is mounted, because it's actually a resonant excitation of the tool. If the tool is a little bit higher, a little bit lower, then it's going to couple differently to the resonant modes that are used for the ultrasonic frequency. And that will actually just renormalize all of your powers a little bit. And so it's not like there's an absolute power that is good, even for the same metal and the same chip, but that there is a good power, but you just have to find it. So that brings. So yeah, Jason, do you have any thoughts on that, or?
Yeah, that's so what happened, because that drove me always crazy, because I also started up in one of these bonders, the let's say the normal ones, is that it always happened after people de-threaded their needle, their tool. Because a lot of them, then they need to, what else is going to happen now, right? They're going to unscrew it, they're going to rotate the wire so they can put it in and then put it back, and they that's what they do a lot of the times. If you do it a lot, you can do it without looking, like back loop, you can get it in. But a lot of people just unscrew that tool, rotate it, and then try to put it back. But of course, the height will change, but also the force on the screw, because that's definitely what's changed your resonant frequency.
Yeah. So I was always hardcore. I never unthreaded never undid the screw.
Yeah, exactly. Just yeah. You have to that pigtail, like without looking, you have to sort of back. Oh yeah, amazing.
Well, I'll come to that in a bit, and that's also a recommendation for our cleanroom bonder that I want to discuss with Lodi, which is that we should really get rid of the deep access tool, because that's like 100 times more difficult to thread than the typical normal tool.
Yeah, keep it. So the nice thing, of course, of deep access, it goes deep. So depending on your package, it depends. You can then still go from sample to PCB and the other way around. With wedge bonder, sometimes the wedge hits the and all these things, but the drag of the wire is way more in a deep access than the wedge bonder. Like you told, drag pulling it off. That's exactly what happens in deep access bonders. It has more drag of the wire.
Yeah. It causes also a lot of headache and a lot of lost time. I think for a low user training level, then I would suggest that probably, unless there's a large proportion of people that need the deep access, I would suggest to actually go away from the deep access as a default setting, and keep the sort of much easier to use non-deep access tool. Okay, but anyway, so yeah, so this is a little bit what I said in the previous slide already. There's sort of a myth of the good parameters, and there's lots of emotion around the wire bonder, because you can totally destroy your sample that you spent a month working on the clean room, and then there becomes shouting matches and accusations that somebody screwed up the parameters. Oh, you screwed up the parameters of the machine. I screwed up my device, and I've lost a whole month. Oh, my point of view is that is that there are no single set of parameters, and anyone who thinks that there is a single set of magic parameters that somebody made once is naive. And so my personal experience is that every type of metal pad requires a different power setting to get it into the good zone. And it's certainly different for PCBs and ceramic carriers and chips. My personal experience is also even the same metal pad that I make on my silicon chip in the clean room will also require me to set a different power setting depending on adhesion quality, depending on how much surface cleaning I did before the depositions and stuff like that. And as I mentioned before, and we discussed now just quite a bit, is that the amplitude of the tool for a given power also strongly depends on how it's mounted. So really, for me, what I always did every time I used the wire bonders, that I always would make sure that I did some calibration to refine the good zone, every time. So, and this was my procedure, how to find a good zone. First of all, the number one thing is make sure you have lots of extra bond pads. Just put like 20 extra bond pads in your material, in your chip somewhere.
You're gonna need them.
You don't want the first bond you make on your sample to be on your real device. That's just a total disaster, because you always have to fit. It's always important to really get the power tuned up right, to have a good bonding experience. And my personal experience, if you spend some time to get to recalibrate and check that get the power right, then it will just work. It will just work, unless it's broken. And then if at least you find out the machine is broken by destroying your test bond pads instead of your real device. I'll go at the end some of the things in my experience that can go wrong with the machine. So my other advice is that there are lots of parameters in a bonder. Well, there's not that many, but there's basically force, power, and time. My advice is that to leave all of the parameters fixed, because actually all of the parameters are cross-correlated. So there's only really one that brings you from this power, from this zone to that zone. And my experience is you can just do that using only power. So to reduce the complication of your optimization process, it's just adjust the power. And my procedure was that I would just lower the power to a power I knew that if you want to really find this whole zone, you can lower the power to a power where the wire doesn't stick, it doesn't stick, and then increase the power in steps. And the West Bond, I would go in units of 10, whatever that was. And then you would just keep notes, and then eventually you'd hit the good zone. And then I would be very curious. I'd go a little bit further on my test bond pads until I hit sort of over squish zone. And then I would go back a bit, like focusing in the SEM, until I was really confident that I hit the optimal power parameters. And then what I would also typically do is, once I have some of my test bonds that I think are in the good zone, I would go in the microscope of the bonder and grab with my special pair of sharp tweezers that I keep in wire bonding toolkit, and give a little tug on the wires just to make sure that they're good bonds. And when that was all done, only then would I start on my real device. And the whole process involves just a bit of testing, but what's super important is that you look at what you're doing and you think about what you see, and you understand what you see. And of course, the other thing I would do is I would always write down the details of what type of metal pads I was bonding on, and the parameters that I found for the good zone. And that was also a good way to see the good zone sort of drifting around a bit. So that's my proposal for the procedure. It sounds long, but if you have the test pads, sometimes I just bring whole test chips of the same material and recalibrate everything every time. And if you know how to use a machine, it takes 10 minutes, and then you can bond for an hour and have bonding, live in bonding paradise, let's say, and not have your devices destroyed. So this is all true if you, aside from one detail, and that is the danger of bad bond pads. So what I described above is assuming that your bond pads are perfect, like you would have on the bond material of a PCB or a ceramic carrier. But there's a problem that the devices we make in the clean room are way outside of the parameters of any typical industrial bond pads that are made by people like Intel. And and they're actually often just not very good bond pads. And there's a particular failure mode that people don't realize and don't identify properly, which is that that actually, when you're bonding, it could be that your bonder is making a fantastic, beautiful bond to the metal pad, but that your metal pad has just a very bad adhesion to your substrate. And what happens is then, when you try to get into the good zone, suddenly your bonds are all coming loose and you get very frustrated and annoyed. But the important point is that actually it's a different failure mechanism. And what I've seen happen many times when I've had bad bond pads is that what happens is actually it makes the bond fine, but because the metal is not stuck to the substrate, during this process of wiggling it back and forth, you actually tear the metal of your bond pad loose, and then you pull out a little bond-shaped circle off of your wire bond pad that you put on your sample. And this is, of course, a failure. You cannot wire. Your wire is not attached to your sample. It's attached to the wire, to the bond pad you made. Just the bond pad, a little bit of the bond pad is no longer attached to your sample. And so the bond is fine. Your pad is detached. And this is a tricky one to solve. But before you try to solve it, it's good to actually recognize when it's happening. And the best way to do that is take a careful look at where you tried to bond on the substrate. And what you will see is a little hole in the metal pad. And if you see the hole in the metal pad, then you shouldn't start blaming the wire bonder, because it's not the wire bonder's fault. The problem is actually with your metal pad itself. And my personal experience is that if you follow the procedure of calibrating the wire bonder properly, I mentioned in the previous page, then 90% of the time, the problem is the pads and not the wire bonder. Now, what can you do if your bond pads are bad?
Sorry, is there, besides changing the power, a shortcut solution?
Well, that's exactly what I'm about to describe.
Oh, okay.
So first of all, I want to say, if your bond pads are bad, the proper solution is to make better bond pads. So, of course, if you've already made your device, there's a hack, and I'll get to the hack on this side of the page in a minute. Don't make the hack your working principle. This is a really stupid idea, but let's say, so first of all, the most important, if you have this problem of holes in your bond pads, the best thing to do is make better bond pads. For that, you can, one of the crucial things is to make sure you have a very good and clean interface and a sticky interface between the metal that you're trying to bond to and the substrate. You can add a sticking layer if you don't have one, like titanium or chromium, if that's compatible with your process. You can also make you can also make your bond pads out of thicker, harder metal. Actually, people tend to think that gold is a great thing to bond at, but gold is very soft. So if you have bad adhesion, gold doesn't really help. But my experience, what does help is actually a hard metal like platinum or gold germanium, let's say a bit thick, like 100 nanometers, because then even if it does detach, it doesn't tear. And then it still is able to successfully bond because the strength of the metal doesn't allow it to tear, and then the force of the bond tool is distributed over the whole area of the bond pad instead of just the area underneath the tool. That's also a little bit of a hack, but it can help a lot by just having big area, by having stiff metals, hard metals in your bond pad.
And just to be clear, this is underneath your circuitry, this layer.
Or on top, it doesn't matter really.
Okay. I would imagine underneath would be better in case you want to have a CPW go from launchpad to device. But
yeah, I mean, most of the metals that we use these days, I must say, are actually like the titanium. We always have clean interfaces, and they're pretty hard to begin with. So the wire bonding is actually generally not a big deal. If you use thinner aluminum, then it can also get sometimes a bit troublesome. But in any case, there are solutions for adding a dedicated bond pad layer, and if you can, then I recommend it. If bonding is your problem, then I recommend. in my nanotube devices years ago, I did always an extra E-beam step just to get good bond pads. And my last tip is that you make sure you have lots and lots of extra area or bond pads that you can test and calibrate your parameters without destroying your device. Now, let's say you're sitting in with the bonder and you start to see holes in your bond pad everywhere, and you're like, oh, I don't want to lose this device. What can I do? There is sort of a hack, and this is my hack, that if you go to low enough power, eventually the wire doesn't stick. So if the wire doesn't stick, it's not going to leave a hole in your bond pad. So my procedure for trying to hack a bad bond pad into coercing it into bond would be to lower the power to as low as possible until I really reach this regime where the wire doesn't stick at all, and then start going up in power. And my experience is that as you go up in power, if you go too high in power, then you have an ultrasonic power where the thing pulls a metal wire off the substrate. If you're lucky, then there's a little super narrow good zone where you can find sort of a fine-tuned power for your specific crappy bond pads that just is good enough to make a bond, but not so bad that it pulls the wire off the metal off the substrate. So that's one tip. The other tip is that if you really are stuck and then you have a bad bond pad, but you don't want to give up on the sample, you can do your second bond on your sample chip, on your sample. Because if you do your second bond on your sample, it's not a big deal if you end up with a slightly over squished bond like this, because you want to break it anyway. And so it's not too bad. If you have bad adhesion between your sample and the substrate, then it's better to do that on the second bond where you're going to break the wire anyway than on the first bond where the force of the adhesion force of your metal pad has to pull the wire and thread it through the tool. And then I also typically, with a manual bonders, did this little trick of pulling backwards to do this table break, it's called, where you actually kind of break off this wire by sliding the tool backwards. That's possible that was also possible even in the West bond, with the semi-automated West bond we had at QTech, where if you push there's two ways to land it. You push 0 or G, and G just goes down and does boom. And the 0 button allowed you to inch down, and then it would only pull up when you let go. And so I could still slide a little bit before I let go and let the tool up. I'm not sure about the one in the clean room. That one we'd have to look at. But in any ways, it's kind of better to avoid hitting, having to do, trying to get lucky with your device after you've done all the clean room work on it.
Would you ever increase the vertical force in this low power setting?
So I've never really investigated, because I didn't have a good way to, I typically found that I could find this good zone with a fixed force and changing the power. I never investigated the two-dimensional phase space of force and power, and it could be that maybe this good zone might get a little bit bigger or wider for different forces. I've actually, I don't know, Jason, do you have any experience in that, or?
Yes, sadly, yes. So it depends. Like you guys also do it. Yeah, you guys also glue your samples on top of the PCB or inside. It depends, but you use some type of glue. Some people even use vacuum grease. Very bad, but okay, whatever. Something sticks your sample to a PCB or whatever. Maybe
it's good to say the reason why you should. It is quite important that your sample is pretty rigidly attached, because otherwise,
yes, it's very important.
Wiggle this, you also might wiggle your whole sample.
Yes, otherwise all the bets are off. Like then you have like rolling the dice all the time, because if you don't have a rigid system, the ultrasonic doesn't make sense for the machine. In my case, I can actually see the PID controller going haywire if something goes, and I use it actually as a tool. I have some other tricks with this fancy, so I can pause in between bonds, blah, blah, blah. And if you just look at your sample and when you are bonding, you can actually see something move. If you see something move, then you're in bad shape, because that means the bond cannot be squished properly. It means that all the energy is dissipated in another piece of the thing you just clamped in, but not on your bond pad. So that means you're going to have bad adhesion or whatever. The nice thing is in my the machine we have something called deformation sensors, and I can actually see with a trick and all these things. What's the problem is if you use it in conjunction with just your eyes in the microscope, you can just see what happens if something moves. You can actually see it in the deformation sensors, and that totally changes your setting. So let's say if you do have problems getting a good bond, for instance, if you glued it crappy, or you forgot to wait long enough, or you clamped it improper, the whole PCB, then for instance, if you do, because you do need a certain amount of deformation in your wire, in this case, in the Bondtech bonders, is about half the wire diameter. So if you see the bond, it will be about, I'll be bond with 25 microns, so it will be between 10 and 12 microns, more or less, is what in deformation we want. And if you cannot reach it, then you're going to have a problem. So, and if already, of course, you haven't done a few bonds, you cannot fix your sample, you cannot reglue it, you cannot this because you're afraid of silver particles. If you use silver paste, will short it up, whatever, doesn't matter. And you might save it by slightly increasing a bit more force. I mean, yeah, physical force like Newton meters or whatever the centinewtons they use in the West bond, I think. I don't know.
I see.
But
so basically, you use the if you're
overcompensating.
if you've hacked it and you've decided to go cowboy style and not attach your samples to anything, then you can kind of hack that by pushing a bit harder.
Yeah, and in this case, because I basically have a robot, because everything is constant, it's not dependent on how much coffee you had that day or how much sleep you got. So I can play with the settings a bit more because it's so constant. So I can see, for instance, if I know that my target is, let's say, 12 micrometers of deformation, I can play with it until I reach it, actually. And that's very hard. There's no measurement. You like you. It's funny because we never work really together, but we do have almost the same procedures. We with same procedures. For instance, the bond pads. I constantly tell the students, make extra bond pads, test it. Every sample is different. Every gluing session is different.
Yeah.
Don't break your fancy sample. Like, and yeah, a lot of them don't follow my advice and they break their samples.
Yeah, so I mean, I guess the big difference, say, of the West bond is that we don't have this deformation sensor, so we have to sort of
use your eyes. You use your eyes,
and you see this sort of squishiness.
Yeah, that's the term I also use, squishiness, to see if you do it properly. And the nice thing is I can make crosshairs with different sizes and whatever, so you can actually see if you want, like if you reach 1.5 millimeter or 1.5 diameter sort of squishiness, because I just made a box around my I make one like a rectangular I have, and I made a box, one which is the size of my tool and one sort of the size of after you have the perfect squishiness. So it's just cheating, but it helps a lot.
Yeah,
it's very handy. Yeah.
So but yeah, so in any case, so it would be, but my experience so far is that usually you can find the good zone with a fixed, assuming that you mounted your sample properly. I would have never dared to wire bond my sample without it rigidly attached to some sort of holder. But assuming that that everything is okay, that I could usually find the good zone, even for the combination of doing the second bond and then pulling backwards to break the wire, and this sort of very careful calibration of the good zone allowed me to, on test bond pads, lots of test bond pads, then I could usually find, just by changing the power parameter, the good zone, even for not so great bond pads. Okay, so then I had that's more or less it.
By the way, what if any of the parts of the wire bonder is dirty? Let's say the tool.
Yeah, so so I had a couple more tips that I wanted to cover that on the last page. So the first, I'm going to say it again and again and again, because you can never say it enough times. Make sure to have lots of test area on your PCB and on your chip where you can test the wire bond parameters without your real device. Use these to calibrate the good zone of your metals, and write down a logbook when you have it. For example, if you don't realize that your sample is not well clamped, but then you find you're in the good zone, but your parameters you find the good zone parameters are going all over the place, bond session, then you may realize that your chip is not clamped properly, or your PCB is not clamped. So my other tip is, as soon as you go in, before you start wire bonding, I would always do a visual inspection of the tip. On the West bond, you can do this pretty well just by focusing zooming in with the microscope and looking at the reflection of the chip. I would actually typically even bring a mirror chip that I made once in a little box, of tools. And I set a chip of silicon with aluminum, and I would just always make a careful look. And the things you want to look for are that the ceramic tip end is clear. You want to actually look at the reflection so you can see that there's no gunk blocking the hole, and to make sure that the tool looks clean, there's no gunk on the sides, and that it's not chipped. Sometimes the tool can become chipped, and if the tool becomes chipped, then the thing that is typically this concave shape that pushes your wire and squishes it a bit is going to give you a weird deformed shape of your wire bonds. And then you can see this, and if you look carefully, and if you see it, you should immediately replace the tool.
I got like one of these dentist mirrors which I could unscrew. I could put it flat.
Yeah.
So you can see the back of the hole and see if there's crap in there, like the PMMA or whatever, which if people bond it on top of their own glue, or the crap which goes into the hole, and this will block your tool. Or
just grease from your fingers or something.
Yes, because they rewired it and they didn't use gloves to rotate the tool. That
can happen. Yeah. So then my other thing is that I would always do myself when I was starting wire bonding is I would test the feed, because it's very important. So the feed is basically the thing that pushes wire through, that works by clamping the wire, pushing it, opening the clamps, and sliding back. And when he slides back, it relies on the frictional force of the wire going through the hole in the tool to make sure that the wire doesn't move when the clamps go backwards. If your clamps are all set properly and your hole of your tool is clean and everything, then it should always just give you more. It should feed out a fixed amount of wire bond tail every time you push the feed button. If it doesn't, that means that there's probably something wrong that you haven't noticed yet about your tip or the clamps. It could be that the clamps are dirty on the inside and the wire sticking to the clamps a little bit, or it could be that the tool is dirty and the wire's kind of getting some friction. If you don't get a regular feed, then something is wrong. Tell somebody and write it in a logbook. Don't leave it. And sometimes, of course, you might really want to wire bond your sample, and then you can kind of work around it and pushing feed like 4 times or something. That's also, probably okay, but make sure that you write it down in a logbook and you let somebody know.
Yeah, or they leave it unthreaded. That also happens a lot.
Yeah.
They made, and then you figure out I always check my tool like you before I put even my sample underneath it, because fancy sample, don't want to break it. Some people work for months on it. Check first that everything works, and then I put my sample under it.
Yeah.
I have another suggestion. If you don't get a proper feed, it might be a kinked wire. So if you pull out a certain length.
Then you open up the clamp and you use your tweezers to check if
exactly.
And then I usually have a pair of scissors and I would cut them off, or you can wire bond it off too.
I do 2 tweezers and I tear it.
I'll pull them. I say, yeah. The other one that I've had sometimes is that the spool has a little bit of a spring friction, and sometimes it would help if I kind of with my finger push the spool a little bit. That was probably an indication of that there was some friction in the clamps or something that was causing a problem. But and then the final thing is that is threading. Threading is an art. I think when I first wire bonded our simple non-deep access tool at MIT, it took me like an hour. Like the first 20 times I did it. By the end of my PhD, I could thread it in like less than a minute. There's a little trick, and I really want to actually show how I would have done it. The best thing to do is to do that in the clean room. We're going to try and get a camera and a video. And actually, Jason, I want to borrow your smartphone adapter for the eyepieces to make a video of all this as well. But basically, you can. It's kind of like threading a needle. You just kind of you can make sure it's straight and smooth, and you just keep sticking it through until it goes. And then
I guess you also do it from the back, right?
I was doing it from the back, yeah.
Yeah, but then do you also then rotate the spool in order to get rid of the slack that way? That's how I always did it. Instead of pulling it all the way through first, I hold it and I rotate the spool back so I get rid of the extra loop I create.
Oh, okay. I always pull it through.
Oh, okay. Yeah, but what happens if I pull it through, that loop usually bends too much and then it snaps. If you know what I mean. And if you unnuts it usually.
Yeah, the biggest problem, the trickiest one is the deep access tool, because the deep access tool, the wire through. And then so my trick of the deep access tool is I would pull it through and then have to loop and go back. But the
no, exactly. I do the same. No.
The loop gets a knot. So what I would do is I would carefully pull it through from the front until the loop was there. And then right before forming a knot, I would stick my tweezers in and try and make it into a little U shape.
Oh, okay. Let's try next time. Try next time that you back rotate the spool.
I see. Okay.
Then you can sort of I don't know. The flow is better for the wire. It's sort of.
I see. But I would still, again, unless there's an absolute need for the deep access tool, and I think that it's actually not really the case for probably most of our clean room users, I would recommend getting rid of the deep access tool as a default, because it just causes a huge headache. And it will make our life and people's experience much better if they don't have to keep threading the deep access tool. I mean, the wire bonder comes dethreaded sometimes. It's just part of life, and you got to rethread it. It just happens sometimes. And if you practice, it's not the end of the world. It's not too hard to do. Good. Those were my tips, and that was my presentation. Questions still from anybody?
So your and my procedures are almost identical. I had an extra what you had with when you pull down your bond pads, right? That problem, that hack you used with. I had another hack which surprisingly quite a lot of time works. Instead of putting a bond which is properly, like if you know for sure this bond is going to stick, you put it dead center, right, on the bond pad. But if you're like, I don't know if it's going to stick, you usually go to a different spot so you have another chance of getting. But if you have the problem that you pull off your bond pad, I actually, if this is your bond pad, I would actually not go in the center. I would actually do a half corner, so it also sticks a bit on the substrate. It's not. But at least you don't, because there's less, the force is now spread also on the substrate and not on your pad. It's electrically it works good enough, but let's say if RF is the thing, then of course it's crap. But at least you don't have your bond pad. If you really need to save it, that's a trick I also.
Actually, you can wire bond on silicon oxide.
Yes, exactly. So you can spread out the force, and it saved quite a lot of pads from people.
Yeah,
it works.
That's another good hack.
And for me, I think it first arose by necessity because of the wedge bonder. And the first slide you showed, you had this package, and it has a very high hull. And the problem is I could actually never go from sample to PCB, let's say that. So from the middle to the outer part, because it would hit the plastic or whatever. But there's another bonus, in my opinion, and I teach it to all the students I have using the bonder anyway, because a lot of the guys also use nanowires and all these things. So ESD is a big problem. So you have to ground yourself and all these things, fine. But I would also advise always go from PCB towards sample, because a lot of the times we have, and you have them also, I'm pretty sure, the ground strips in your samples that are short. Well, the ground strips is wrong. It's shorting strips. So all the paths or all your connections are shorted together, so they're the same potential.
You know who invented that? In Delft?
Oh, okay. Well, we have a lot of problems. So I have a lot of tips and tricks for. Well, we had a lot of problems in that, but so that's also a reason why we would go from PCB to sample. So you minimize the risk of ESD anyway. But also, let's say if you're, and because usually the bond your first bond, if you go on the first bond on the PCB, that's usually the easiest one because they're fat. You have multiple chances. They're thick, so you never pull them off. So also, in my opinion, like if that bond doesn't, so also if your first bond fails, there's no reason for you to touch your fences. So I would also, and the nice thing is, that's a nice thing about the analog bonder, because that's standard, because you are moving the bond tool and the machine for you. The machine we have is so fast, you cannot even pause it unless you put it on the pause sort of setting.
Yeah.
The nice thing is, if my first bond fails, I would stop and try again, because why touch your fancy sample? So that's sort of the extra bit I always teach when I teach procedure of try to always, if you can, go from PCB and then towards your sample. Of course, if you want to find the magical zone in the of course you do for instance, maybe first a few bond pads on those extra bond pads you have. You can find the stickiness with the extra factor of the friction of the tube of the feeding of the wire. Because then you can compartmentalize really on the settings, and then of course it will change when you go from A to B. Then you know it's not the stickiness problem, it's more of a friction problem or whatever. That sort of helps maybe narrow down some problems which might arise.
Good. Okay. Good. Then, if no, I can't see my mouse anymore on the Zoom thingy. How peculiar. I had to guess where I'm clicking. Anyways, if there's no more questions, then I propose that we close this one out. Going once, going twice.
No, thank you.
Good, great. Then what I'll do is I'll stop the recording. We'll put this on. If nobody minds, I'll put this on YouTube. I think it's a very useful thing to share with people, this type of information and discussion. And hopefully we'll follow this up also, probably for me after the 21st of September, with also a sort of a session in the clean room where we can take a look at all of these, how to do this on our bonder and